the velocity at that specific orbit. That will be the velocity of the International Space Center. Any questions on how to get the orbital velocity? Very simple. You pairs gm over r squared with mv squared over r. Cancels out, you get p. This will be how to get p at a specific location. How can we compare the velocity at two orbits? If this is orbit 1 and this is orbit 2, we just go to this equation and we can set that v squared 2 over v1 squared will be inversely proportional, but now not to the radius, because v squared is equal gm over r is inversely proportional to the radius, not to the radius squared, v squared. So I can say that the ratio of the velocity squared will be equal to r1 over r2 squared. This is just to get the, sorry, my bad, r1 over r2. This is how to get the relationship between two different velocities at two different locations. Good. Where will be the orbital velocity? Where the satellite move faster? On the inner orbit or on the outer orbit? In the inner orbit. You can see from the equation that on the inner orbit, the satellite will move faster than on the outer orbit. Okay? Good. That's the second topic, the third topic. Force, gravity, orbital velocity. So if you want to find, now the third topic will be the Kepler's law, or the fourth. Kepler's law. Kepler's of planetary motion. The Kepler's laws of planetary motion. There are three laws that we will study here. The third one, I will put emphasis on the third one. The first one said we will do calculation only with the third one. This is just a concept. The first Kepler's law said that if we put the sun, all planets move in an elliptical path. If this is the sun will be at a point that is called the focal point or focus. Focal point, and all planets will move in an elliptical path. So the centricity is close to 1, which we can say that is almost a circle. But most of all planets move in an elliptical path with the sun at the focal point. Number one. Number two, Kepler said, after he studied the Tycho Brahe, which was the professor, his professor, when he was doing the doctoral study, Brahe died because he was alcoholic, and Kepler got most of the work, and he finished the work of Brahe. For this reason, it's called the Kepler's law, not the Brahe law. But Kepler was who finished all the work of Tycho Brahe. But the second law said that if this is the sun, and this is the planet, example the Earth, and we trace an imaginary line from the sun to the Earth, or to whatever planet, this imaginary line, which is called radius vector, will sweep in equal amount of time, let's say 1 day, here, at this point, when the Earth is here, it will sweep in 1 day the same area, this area, and this area will be the same. Not wrong to scale, of course. So, in 1 day, this is due to the angular momentum. I won't prove this. The third law, which is the one that I will use here, said Kepler said that the ratio of the square of the period is the time to complete one full revolution. The square of the period divided by the cubic of the distance or radius, the distance from the sun to the planet, for all planets in the solar system, will be equal. I am assuming that all are moving in a circular path at this moment, to not use semi-major axis of the ellipse. I will use the radius. They will be constant, and that constant will be Kepler constant for the sun in this case, because the sun is the central body. In other words, if we have the sun here, and this is one planet, the other planet, if I take the time to complete one full revolution, that is called, for the Earth? Yes, period. And what is the period for the Earth? A year. So if I take the period of the Earth about the sun, which is 1 year, and I divide by the distance from the Earth to the sun, cube, this will be constant for all planets on the solar system. And that constant is the Kepler constant. How did he prove this? Using this formula, B squared is equal to what? B squared is equal to Gm over R. In this case, will be the distance from the planet to the sun. On the other side, we know that V is the distance over time. If the Earth is moving in a full circular path, how much is the distance covered in 1 year? If it's a circular path, what will be the distance covered by the Earth in 1 year? It's a circle. 2 pi r. So 2 pi r over what? How much is the time to complete one full circle? Which is, how did I call? How did I label?
1 year.
Yes, what is 1 year for the Earth? What is that? Physical magnitude.
1 revolution, 1 period.
1 period. Period. T.